Okay, so we're going to do some more exponential modelling. And I've said you're going to need to use your skills of solving equations from chapter 14 in modelling scenarios. This first question that I've got here is really similar to the modelling types of things that we did earlier on, but the remaining ones are including solving equations. And it's interesting, for the ones that include solving equations, there is no specific exercise on this, but there are many exam questions on the topic, and I'm going to include them here. So I'm going to do this one as a recap, the next one is a demo, and then you can also try some of the other ones in the remaining part of the video. So this first one that we've got, it says the mass m grams of a radioactive substance t years after being observed, so it's m grams and t years, is modelled by this equation here. And you'll notice that the power is negative, so we know that this is actually referring to a decaying. And we could also say that this point here is going to be 25 when t is equal to 0. According to this model, find the mass of the radioactive substance 6 months after it was first observed. So be careful here because it's measured in years. So when we say 6 months, we're going to have to say that time is half a year, or 0.5. So let's find out what the mass is. The formula says that the mass is 25 e to the minus 0.05 multiplied by 0.5 for t, okay? So that's going to be 25 multiplied by e to the minus 0.05 times 0.5. And we get that the answer is 24.4 grams to 3 significant figures. It's always useful giving it to 3 significant figures. Only 2 marks, so nice and easy. Part B then, like we did earlier on in this topic, we're going to find out what dm dt is. So we're going to differentiate it. Well, the 25 is going to stay there. And then we're going to multiply by that the coefficient of t, which is 0.05, and we've got e to the minus 0.05t. Now, rather than multiplying these two things together, because they're saying that it is going to be in terms of m, it's worth noting that this 25 and e to the minus 0.05t, those two things make up m. So I could just rewrite this as minus 0.05 m, which means that k is minus 0.05. Okay, so no need to have multiplied those bits because we noticed that the 25 and the e to the minus 0.05t is what m actually is. So nothing different here, but you're going to see in the next question that it's going to include some other things too. Let's just check we got these right. So we've got 24.4 grams and minus 0.05. Okay, this is where it doesn't have some of these things in the textbook, and you're going to need to know how to do them still. The growth of pondweed on the surface of a pond is being investigated. How exciting. The surface area of the pond covered by the weed, a meters squared, can be modelled by this equation. So one of the things I'm noticing is there's a positive power up here, which makes me think that there is going to be exponential growth. If I was going to draw a graph of this, there's going to be some kind of growth, and it's going to be crossing at 0.2, where t is the number of days after the start of the investigation. Notice that a is measured in meters squared. It says state the surface area of the pond covered by the weed at the start of the investigation. In other words, when t is equal to 0. So for part A of the question, the surface area is going to be 0.2 multiplied by e to the 0.3 times 0. So it's just going to be 0.2 meters squared. When it says the word state, you can just say it without doing any calculations at all. Part B, find the rate of increase of the surface area of the pond covered by the weed in meters squared per day exactly 5 days after the start of the investigation. So we're going to say that t is equal to 5. And here is that word we've come across so many times, rate. We want the rate of increase of the surface area of the pond. And there's also this clue here where we've got the area per time. So that's actually asking rate of increase is going to be dA dt. So let's just write down the area is equal to 0.2 e to the 0.3t. So I'm going to start off by finding the rate of increase. This thing here is the rate of change of A. So I'm going to do 0.2 multiplied by 0.3 e to the 0.3t. And they have said that t is going to be after 5 days. So dA dt is going to be 0.2 times 0.3 times e to the power of 0.3 times 5. And I'm just going to whack that in my calculator. 0.2 times 0.3 e to the power of 0.3 times 5. So we get 0.269 meters squared per day. Let's check that's right. Yep, so we've got meters squared per day 5 days afterwards. So it means after 5 days, it is growing at a rate of nearly 0.27 meters squared per day. And that's going to be faster than when it first started. Then it says, given that the pond has a surface area of 100 meters squared, find to the nearest hour the time taken according to the model for the surface area of the pond to be fully covered by the weed. So the surface area is 100, and we want to find out what the time is. Well, what's the thing that connects together the area and the time? Well, it's the formula. So we're now going to do the bit that's new that they don't mention in the textbook, which is modelling using the equations. So the area is 100, and we're going to find out what the time is. So I'm going to say that the area is 100, and we know that the equation, or the formula, sorry, is this. And we're going to use this to find t. So 100 instead of a equals 0.2 e to the 0.32. So I'm going to do 100 divided by 0.2, which is 500. So I get 500 e to the 0.3t. Now I'm going to take ln of both sides. So I'm going to do ln 500. When I do ln of this side, I'm just going to get 0.3t. And so t is going to be ln 500 divided by 0.3. ln of 500 divided by 0.3, which is 20.7 days. Seems reasonable. It's going to fill up the whole pond in 20.7 days. Part D of the question says, the pond was observed for 1 month. By the end of the month, 90% of the surface area of the pond was covered by the weed. Evaluate the model in light of this information, giving a reason for your answer. So we've just said that we think it's going to take 20 or 21 days to cover the whole pond. But someone's been watching it, and at the end of the month, only 90% of it has been covered. So when it says evaluate, it's saying, is it a good model or a bad model? Well, I don't think it's a very good model, because our model says that it should be covered by the 21st day, and it's still not covered by the end of the month. So I think we should just write that down. Our model suggests the pond would be fully covered by the 20th or 21st day. But observations show it still isn't covered after a month. So the model is not very accurate. So there's just this little extra bit here of wanting to do an equation, which we couldn't do previously, and some kind of comment about the model. Let's see the answers. So we got 0.2 correct. We got the 0.269, which we have here. We got the 20 days and 17 hours, which is the same as 20.7. Did it ask for it to be given in days and hours? Ooh, it does say find to the nearest hour. So I probably would have lost a mark there. So we're going to have to do this 0.7 hours. Let's quickly go back to that. So I'm going to go back to this. I'm going to take off the 20 hours and I'm going to multiply it by 60. Not by 60, by 24. So it's actually 20 days and 17 hours. I would have lost the mark because it asked for it to the nearest hour. I guess I also could have just gone to the previous bit, which was the That was my answer, and I could have just multiplied it by 24. So I could have said it was 497 hours if you wanted to see it in that way. That was a conversion between days and hours. So I would have lost that mark. And it says, their bit says, the model often given suggests the pond is fully covered after 20 days and 17 hours. The reserved data is inconsistent with this, as the pond is only 90% covered by the end of 1 month. Hence, the model is not accurate. Okay, I think you should have a go at doing this one without me. And then you can pause it, try it, and then see how it goes when I go through them. Okay, so the value of a car can be modeled by this equation. It's just telling you that time is the real number and time is positive here, where this is the age of the car in t years. T years and v is in pounds. Find the initial value of the car. Initial value is when t equals 0. So v is going to be equal to 15,700 multiplied by e to the 0, which is just 1, plus 2,300. So 15,700 plus 2,300 is 18,000. So the initial value of the car is 18,000. Seems kind of reasonable for the price of a car. Given that the model predicts that the value of the car is decreasing at a rate of £500 per year when t equals t, show that this thing is true. So there's some key words here that I want to look out for. First of all, it says that it is decreasing at £500 per year, and it says rate. As soon as I see rate, I think dv dt. So I think that it is dv dt is equal to minus 500. Now the reason it's got the minus in here is because if something has a negative rate, it means that it is decreasing. So I'm going to write that down. I'm not going to even think about this for a second. I'm going to ignore this for now. I'm actually just going to try and think, what can I do with this information that I'm going to highlight here in green? So the original equation is v equals 15,700 multiplied by e to the power of minus 0.25t plus 2,300. And I know that dv dt is minus 500 because this is the rate of change is a decrease of £500 per year. So I think what I can do is I'm going to differentiate this. If I differentiate this with respect to time, I will get dv dt, and then I can compare it to this thing. So when I differentiate this, I would have 15,700 multiplied by minus 0.25 e to the minus 0.25t, and this thing is just going to go. So dv dt is equal to 15,700 multiplied by minus 0.25, so that's minus 3925 e to the minus 0.25t. Now I know that dv dt is equal to this and this. So I'm going to take those two things and I can say they're equal to each other. So minus 3925 e to the minus 0.25t is equal to minus 500. And look, that's so close to what we've got. The only difference is our one has a negative in front, so we can just get rid of the negative. We can multiply both sides by negative 1. And this was the equation that they wanted. Pretty tricky question, but I've given you that clue a few times. If the word rate is there, it means something dt. Okay, it then says, hence, find the age of the car at this instant. Oh, I guess I should say that t is equal to t at this point. So I should have said 3925 e to the minus 0.25t. This is when t equals t. But it's pretty subtle. It's really the same thing. So we want to find the age of the car, giving the answer in years and months to the nearest month. I'm not going to make the same mistake as the previous question. So basically this just means for part C of the question, or part C, B part 2, excuse me. This was part 1, this means part 2. We're just going to solve the equation. I'm going to take this and I'm going to solve it. So it's 3925 e to the minus 0.25t equals 500. Well, I'm going to divide by the 3925. So that's 500 over 3925. And I'm going to take logs of both sides. So when I do the ln of this side, I would get minus 0.25t equals ln of 500 over 3925. So t is going to be equal to the ln of 500 over 3925 divided by minus 0.25. That's weird that we're dividing by a negative. Makes me think this thing has got to be a negative so that overall time becomes positive. Let's see. So we're going to do the ln of 500 divided by 3925. Good, it's negative. And I'm going to divide that by minus 0.25. So we get that the answer for t is 8.242 years. Let's now keep going. So we need that in years and months. So it's clearly going to be 8 years, and we've got 0.242 years as the second bit. So if I want to convert this to months, multiply it by 12. So let's take the 8 off, and let's multiply it by 12. So it's 2.90 months. So it is going to be 8 years and 3 months. And that's to the nearest month. 8 years and 3 months. Okay, we're nearly there. We've done most of the hard work on this question. It then says the model predicts that the value of the car approaches but does not fall below A pounds. State the value of A, and then state a limitation of this model. So I'm going to write down the equation again so that we've got that to think about. It's that the value of the car is 15,700 e to the minus 0.25t plus 2,300. Now, if you imagine what this is going to look like as a graph, as a transformation, well, this bit, this adding on 2,300 has shifted the asymptote that is usually here. It's moved it so that it's 2,300 up. And we also knew the initial price of the car. We said that the initial price of the car was 18,000. So if you think about what this looks like, it's crossing at 18,000. And we've said that the asymptote has raised up to the line 2,300. So as t becomes a big number, as t increases, we think that the value is going to go towards 2,300. And I'm going to say that in another way. Let me just check what the question is. It said state the value of A. It approaches but does not fall below A. So we're saying that the answer is going to be 2,300. And you can see how it would approach this asymptote, but it would never actually go below it. So another way you could think about this is you could say as t becomes a really big number, as t becomes infinity, we can find out what v is going to become. Now, when I say infinity, you can just put in your calculator. Why don't we just say that t is like 1,000 years and see what we get? So if I put it on my calculator, if I do 15,700 and I multiply it by e to the power of minus 0.25 and I times it by 1,000, and then I'm going to add to this number, the 2,300, you can see that it's going to get very close to 2,300. So as t becomes a really big number, v is going to go to 2,300. Hence, the value of the car that it tends towards is going to be £2,300. The last thing that we need to answer is it says state a limitation of this model. So the model here is just taking into account the age of the car. It's the only thing that it's taking into account. So that's probably not very realistic. So a limitation could be, is the model doesn't take into account the mileage or condition of the car. That's one of the things you could say. You could also say that over time, it's likely that the car could become like a rare car or a vintage car. So maybe the price actually would later on, the graph might do something like this. It might like increase in price. We don't know what's going to happen. So that's one of the limitations here. Okay, so we got 18,000. We came up with this. We got the 8 years and 3 months. We got the 2,300. And other factors may affect it, or the price may rise as the car becomes rare. I'd say this is kind of one of the hardest bits, but this bit really was like a way of thinking about like transformations of graphs. Or you could think about this kind of stuff of plugging some values into your calculator. So in the next video, I'm going to do 2 more questions. The 2 questions that I think you should probably have a go at though, if I can find out where I'm at the moment, is going to be this one. So you might like to pause the video and have a go at doing this yourself. And then you can see in the next video me trying it. And then the last one I'm going to do is this one here. Seeing as there aren't any questions like this in the exercise book, I just think it's good for you to have a bit of a practice. Okay,